Hello, students. So for something different, what if we changed it? So earn I has to hold at least I balls. Okay, so now what would we get? Well, we'd get earn 1 would have to hold at least 1, so x to the 1, x squared, x cubed, and so on. Earn 2, well, that would be 2 and up, 2, 3, 4, and so on, and then and so on and so forth. And then finally earn k, well, x to the k plus 1, and x to the k plus 2, and so on and so forth, because our choices are k balls, k plus 1 balls, k plus 2 balls, and that goes on and on. So this is just going to be x times, well, the normal geometric series formula, so x over 1 minus x. And this is that. And this is going to be that. Okay, so what do we have here? Well, we will have the product from I equals, let's see, we'll start with 1, and we'll go all the way up to k of x to the k over 1 minus x. So that's our generating function for the at least eyeballs case. And of course, we could play around if we want to in Python. Let's enter some of that. I'll pause so you don't have to watch me type. Okay, so you will see here that if I go out, I just entered the new generating function using prod, and you'll see if I go out 20 turns, I'm not going to get anything because I can't just place 20 balls if I have 10 earns, because earn I must have at least I balls. So I have to go out to actually 55 if I'm going to do something like 10 balls. And you'll see this is a much simpler function as well than what we had. But this does seem correct. You can reason your way through these various terms. For example, suppose I wanted to put 56 balls in my earns and I have 10 of them. Well, I have to put the minimum amount in each one, and then I'm going to have 1 ball left over, and I'm going to have 10 choices for where I put that ball, and anything is okay. So that's how I get 10 there, and you can sort of reason your way through some of these other coefficients as well. So that's an example of a slightly different restricted earn counting problem. Now let's try something else. Okay, let's talk about partitions. So let's say we want to partition n into parts. So the number n. So basically any number of parts. So we introduced this notation earlier for the number of ways we could partition n into k parts. Now what we're interested in here is the sum of all of these together for any possible k, as k ranges from 1 to n. So any number. Okay, well, let's think about that. Well, if I'm going to partition n into parts, what are my choices? Well, I'm going to need a certain number of 1s and a certain number of 2s and a certain number of 3s and so on. And the order doesn't matter, it's just the total number of 1s. So basically for the total number of 1s, which I could think of this as a 1s jar. So I have something like this for the 1s, and then for the 2s, I could either have 1, 2, or 2 2s, and so on. This is a lot like the change problem. x6, x to the 9, and so on, and so forth. And this goes on. Forever? Does that make sense? Could we come up with one function that works for all possible n? Well, let's think about it. Now remember, the important thing when we're dealing with these generating functions is that each of the coefficients can be computed in a finite number of steps. As long as we have that going for us, I'm comfortable with us using it. So let's see. Okay, suppose I wanted to find, say, the coefficient of this, of let's say, I don't know, let's say x cubed. Okay, so let's say I wanted the coefficient of x cubed. Well, let's think about this. As soon as I get past this term, my choices are going to be 1 plus x to the power something bigger than 3. So I'm going to have to choose one from each one of these. So after this point, all my choices have to be 1. But what does that do? Well, it makes the number of possibilities finite when I'm sort of adding things up. So basically, I could take the x cubed here and a 1 and a 1. Or I could take a 1 here and an x squared here and an x. Or I could take a 1 here and a 1 here and an x cubed. So that's true for the coefficient of x cubed. I'll even write that out. So what did I say? I could do 1 times x cubed times, and then these are all 1s. Or I could take x times x squared times 1 and all 1s. Or I can take x cubed times 1 and all 1s. And that's it. And the same is going to be true for any coefficient. Because let's say I want to pick out the coefficient of, I don't know, x to the 10, right? There's going to be, at some point, I'm going to have 1 plus x to the 11, and I can't use that. So when computing the coefficient of x to the 10th, there's going to be finitely many things that I'm putting together. Okay? And what did this correspond to? Well, this corresponded to the partitions of 3, which were 3. This corresponded to 3, this corresponded to 1 plus 2, and this corresponded to 1 plus 1 plus 1, which is exactly what I got. So it makes sense for us to add this together. So what could I do? Well, I could think about this as the product of 1 plus x to the k plus x to the 2k, and so on and so forth. And what am I starting with? Well, I'm starting with k equals 1 and going all the way to infinity, which I can even simplify further because we have a formula for this, right? This is just like you plug in x to the k into the geometric series. So 1 minus x to the k. So, what if you also wanted distinct parts? Well, if we want distinct parts, then what are my choices going to be? Well, I can only have at most 1, 1. So I either don't have a 1 or I have a 1. I don't have a 2 or I have a 2. I don't have a 3 or I have a 3. And I don't have a 4 or I have a 4, and so on and so forth. So what am I going to get there? Well, I'm going to get the product starting with 1 to infinity of 1 plus x to the k. And one more time, does this make sense? Well, let's say I wanted to say pick out the coefficient of x cubed here. I can't choose a 1, or I can't choose anything but 1 from every term after this. So basically, I'd be either choosing an x cubed and a 1 and a 1, or I'd be choosing an x squared and an x, and all 1s. Those are the only ways I can make it, and those correspond to the 3 and the 1 plus 2. But notice the 1 plus 1 plus 1 is not possible because this stops. It's either I include a 1 or I don't include a 1. So yeah, those are some examples. Maybe getting a little creepier if you're really into things looking finite, but each of these coefficients can be computed in a finite number of steps. So this really is a finite process. So nothing to be scared of there. And those are two more interesting, hopefully interesting examples.